Welcome back. Today I wanted to look at the kinematics of bike gears. So here you can see a bike. There's a 19-tooth gear in the back and a 43-tooth gear up in the front, the chain ring and the cog. The cog is actually connected to the wheel, and this is a fixed gear bike. So the faster the bike is moving, the faster the pedals are moving. And the pedal motion is called the cadence. So the more the pedals are spinning around, that's a higher cadence. And then the bike wheel itself is controlling the speed of the bike. The faster the bike goes, the more the bike spins, and the higher the cadence. That's how these fixed gears work. These were the original safety cycles as compared to the old bone shakers with one giant wheel and two pedals directly fixed to the axle of the wheel. Let's take a look at how to choose the cog and the chain ring, or even just if we know the cog and the chain ring, what would be a typical speed for a normal cadence of 60 RPMs or 1 rotation per second. Here we have a fixed gear bike. It consists of a cog, a chain ring, and then the wheel. However fast the cog is moving, that's how fast the wheel is moving. And the chain ring itself is attached to the pedals. So here these are the cranks, and out here is the pedal. So the faster the chain ring moves, the faster your feet are moving. That's called the cadence of the bike. And back here, the cog on this bike in particular, on my fixed gear, I have a 19-tooth cog, and then I have a 43-tooth chain ring. So let's come down and take a look at the kinematics of what's going on here. This system is totally constrained, that if the cog is moving at a certain speed, then it determines the speed of every other component. Or if it's accelerating, then every component is accelerating. So what we're going to do is say that I'm pedaling the bike at an omega. We'll call this B, and we'll call this A. That omega B is 60 rotations per minute, which is 1 hertz, 1 cycle per second, or also 2 pi radians per second. So that's how fast I'm pedaling the bike. And what I want to know is how fast is the bike traveling. This wheel, it's a 700 by 23C tire, which means that the diameter is 668 millimeters, and we're going to use the radius, so radius of the wheel is 334 millimeters. Now, I don't know the radius of the cog or the radius of the wheel, but I don't actually need to. We're going to use the same thing that we did for those interlocking gears. Here we don't have a constraint that they're interlocked, but we do have a constraint. If I call this point A and this point B, so that's why I called it A and B like that. And I'll call this I'll give this a coordinate system, this A1 and A2, and I'll give this a coordinate system along here, this B1 and B2. And these are just where the chain is connecting to the top of the gear. So if I want to describe the position, so I'll call that A, and I'll call that position B, or maybe little a and little b. So the position of A is equal to the radius of that cog times A1, and the position of B is the radius of the chain ring, so RB times B1. Now the constraint on the system is that the velocity with B with respect to A has to be 0. If it's anything other than 0, then the chain is either stretching or compressing. And either way, we don't have a chain that's under tension. So the fact that the chain is under tension, this distance has to remain constant, which means that A and B have to remain, the relative velocity of A to B has to be 0. I'll continue down here. So VA is equal to negative RA times omega A2, and VB, use that lowercase here, is negative R B omega B times B2, because the derivative of A1 is negative A2, omega times negative A2, where omega A and omega B are how quickly the chain ring and the cog are spinning. Now let's plug in our constraint. VB equals VA plus VB to A. But this term we already said was equal to 0. So now R omega A equals RB omega B, or a 19-tooth over 2 pi RA times RA omega A equals 43-tooth divided by 2 pi RB times RB omega B. So total teeth around the circumference, so teeth per circumference times that RA omega A, which leaves me with my relation that omega A has to be 43 over 19 times omega B. And they both have to be spinning in the same direction. If the chain ring is rolling forward, as drawn here, then the cog is also rolling forward. It would be a little strange to pedal backwards to get forward. So now plugging in my 1 rotation per second, 2.26 times 1 hertz is equal to 2.26 rotations per second, or about 2.3 times faster. But how fast am I riding? That was the question. I don't care how fast the wheel is spinning, I just want to know how quickly I'm moving down the street. For a bike, if the cog is spinning at omega A, that means both wheels are also spinning at omega A. In order for this wheel to maintain our kinematic constraints, if the cog is spinning at 2.26 rotations per second, then the wheel itself is spinning at 2.26 rotations per second. And the distance that my bike is going to move is equal to the radius of the wheel times the angle of the wheel, so the change in the angle of the wheel. And that's along that I direction. So if I take a derivative of this, the radius of the wheel is constant, and I get velocity, so the speed of the bike is going to be r of the wheel times theta dot of the wheel, which is omega a. So V is 0.334 meters. That was the radius of that 700 by 23 wheel, times 14.22 radians per second in that I direction. So V is 4.74 meters per second I. Or another way to say that is that it's about 10.6 miles per hour. Perfect. That's a great speed to cruise to the beach on.